As we wrap up this unit of study, I want to point out that Newton's law of universal gravitation is just one of the first of many inverse squared laws that you'll encounter in your study of physics. So Newton's law of universal gravitation, as you're well aware by now, says force of gravity can be calculated by multiplying a universal constant times the mass of one object times the mass of a second object divided by the distance between the two of them squared. If we really want to properly make this a vector equation, force is a vector, so to make the right side of the equation a vector, we can tack on an r as long as it's r hat, as long as it's a unit vector that doesn't change the magnitude of the outcome. If we want to express something known as the force per unit mass, then we have a quantity known as the gravitational field strength, and it's equal to gm over r squared, and again we can make this a vector equation. Well, in the future, in your study of electricity and magnetism, particularly in electrostatics, you'll learn about Coulomb's law if you haven't already, and it says there's a force between charged objects. If you rub a piece of plastic with wool, invariably you strip away some electrons off of one material and onto another and create net charge on both of them, and the positive charge and the negative charge have a way of attracting one another. That force is equal to a universal constant. Here we use the letter K instead of G. The symbol for electric charge, instead of amount of mass measured in kilograms, electric charge is symbolized by Q. It's a quantity measured in coulombs. If I multiply the number of coulombs of charge in one object times the amount of charge in a second object and divide it by the separation of the two objects squared, this represents a way to calculate electrostatic forces. Force is actually a vector quantity, so to make the right side of the equation a vector quantity, I need to throw in an r hat. If I want to know the amount of force per unit charge, then I'm calculating something known as the electric field as opposed to something like gravitational field, and it's equal to kq over r squared. A wire that carries an electric current, especially a small segment of wire, if we just identify just a short length of this wire and say that bit of length represents a vector ds, if there's an electric current flowing to the right in this wire, we symbolize electric current with capital I. So current number 1 flows to the right in this wire, and there's a second wire parallel to it, just below the first wire. And it also carries some amount of current flowing to the right. We'll say that amount of current is I number 2, and that current flows through just a small region, ds. Then this region of the wire and this region attract one another. They don't attract in the same way that masses attract. They don't attract exactly in the same way charges attract. They attract in the way currents attract one another, but that can be expressed in the form of an inverse squared law. The amount of force is equal to a constant. We'll just call it, well, yeah, I'll write in the constant. It's mu naught divided by 4 pi, for whatever that's worth. Okay, then multiplied by, in this case, it's the product of current and displacement. So I1 ds, and instead of just writing it as multiplication, since ds is a vector, I need to decide whether this is a cross or a dot product. Well, force is a vector, so it shouldn't be a surprise. This is a cross product in this case. And then if I multiply I number 2 ds and divide by the distance between the two wires, quantity squared, you can calculate the force of attraction between two wires. That's known as the Law of Biot-Savart. So there you have it. Inverse squared laws show up a lot, and they describe some of the very fundamental forces of our universe. So your study of inverse squared laws does not begin and end with Newton's law of universal gravitation.